let's prove Euler's criterion, which says that the Legendre symbol of a over p is congruent to a to the power of p minus 1 over 2. Basically what this says is if a to the p minus 1 over 2 is 1, then a is a quadratic residue mod p, and if a to the p minus 1 over 2 is negative 1, a is a non-residue mod p. So first, let's assume a over p is 1. We know it has to be either 1 or negative 1 by the definition of the Legendre symbol. And so therefore, there is an x such that a is congruent to x squared mod p. Now let's consider a to the p minus 1 over 2. That's the same as x squared to the p minus 1 over 2, which is equal to x to the p minus 1, and that is congruent to 1 mod p by Fermat's little theorem. This is, of course, assuming that p does not divide x, and this is true because of this equation. P can't divide x because p does not divide a. Okay, and that proves half of it. Now let's assume a over p is minus 1, so we got to show that a to the p minus 1 over 2 is negative 1 in this case. So again, we have that p does not divide a, so a to the p minus 1 is congruent to 1 mod p by Fermat's little theorem. And now let's consider the equation x to the p minus 1 over 2 minus 1 is congruent to 0 mod p. By part 1 above, we showed that all of the solutions to this equation are quadratic residues. Okay. And furthermore, we know from the polynomial roots theorem, which I'll just call polyroots theorem, there are at most p minus 1 over 2 solutions to that equation. So we have that there's p minus 1 over 2 solutions, and all of those solutions are quadratic residues. Okay? So now let's say this. A to the p minus 1 is equal to a to the p minus 1 over 2. Oh, sorry. This should be a minus 1 here. A to the p minus 1 minus 1 is congruent to 0. We have that from this. Let me rewrite that so it's a little bit more clear. So we're going to subtract 1 from both sides of this. So a to the p minus 1 minus 1 is congruent to 0, but we're going to factor this. So a to the p minus 1 over 2 minus 1 times a to the p minus 1 over 2 plus 1. And we know the solutions to this are exactly the QRs, the quadratic residues. And since we are assuming that a is a non-quadratic residue, then this is non-zero, and so we must have that a to the p minus 1 over 2 is congruent to negative 1, because this must be 0 to satisfy this equation. It is congruent to 0 by Fermat's little theorem. And so we have shown that a to the p minus 1 over 2 is negative 1 if the Legendre symbol is negative 1, and that completes the proof.